Sorry about the delay. I had to figure out that my VGA adapter was still in the other room. But hey, yeah. You want to introduce me or shall I do it myself?
You may do it yourself. The last topic of today, but Rudi already introduced all
Wait for the applause till you've seen what you are about to get, and then you can decide whether you scream applause or not. Okay. Yeah, we just had this talk about the Raspberry Pi, and as an electronics engineer, I'm also kind of like obsessed with small pieces of electronics that you can build stuff with and connect it to the network, connect it to the computers, that kind of stuff. So around my kitchen table, I decided, well, do some experiments in the area of the Internet of Things. I want to talk a little about sensors and actuators that I connected to small pieces of computing. I will talk about connectivity, how to connect that, because it's all about building networks and connecting stuff to other interesting pieces of computing. So do it yourself, and I will show you how simple it is to actually go from, hey, I got something working on the screen, to, hey, I got something that's actually doing something in real life, like opening a door, or turning on the light, turning off the light, let the robot walk, or just see whether it's raining outside or not, and that kind of stuff, and how you can like use that also in your real work life, because monitoring the data center, that's something we like to do, and we buy all kind of heavy, expensive stuff for. But you can also, if you got the small data center, not that much money to spend, you can also build it yourself and get it rolling with, well, from your kitchen table. So, the Internet of Things, that's kind of like buzzword bingo. If you read an article about the Internet of Things, your buzzword bingo card gets full, well, within the first 3 sentences. It's Internet of Things. It's gonna change the world completely. It's hot, and it's robotics. It's artificial intelligence. It's computer vision. It's gonna change your life forever. It's, well, everything. And the example that they take is, like, if you have your fridge connected to the internet, yeah, what? Right? I know what I put in that fridge, and I really want to know myself, because I can smell whether the milk is bad or not. And we're far away off from that, and hey, who needs that? But the buzzword bingo is there. So, some examples, sensor networks. A couple of years ago, the Internet of Things was like, hey, we do sensor networks. We gather data. We have sensors everywhere, and that's connected to the internet, and then we have data. But now, with the Internet of Things, we also can do some actuation. We can change things. We can open the door. Hey, if I press this button, the door in my house opens. Hey, great for that burglar that's there. But hey, that's how the sensor networks evolved to actuator systems, and combination of that, like if it gets too hot, you should turn on the fan, and with the Internet of Things, you can actually program that. For example, home heating systems have thermostats, and right now, every every major energy company or every major heating appliance company has that internet connected thermostat that you can use for, hey, I'm leaving right now, so, well, turn on the heating so when I get home, it's warm. Well, that's kind of like, hey, that might become handy. That's a combination from the sensors with the actuators, turning on and turning off the heating. And that's becoming something that, well, can be useful. So with all that, that doesn't work if you just don't have networking. So those small computers that do that locally processing thing and getting the sensor data all have networks and all have, well, have been connected to a network, to the home network with a piece of UTP or wireless, or it's connected to the network in a mesh where it sends data to other small appliances that are gathered around your house or in your house or around a certain area that relays data onto the gateway that goes onto the internet. That's just one step from point to point to having a mesh environment where actually the network organizes itself. Hey, you got 20 sensors and actuator things, so I glue something on the door that can open the door, I glue something on the wall that measures the temperature. And I don't have to bother about networking, they connect to each other, and well, there's one pretty close to me, my internet router. Hey, that one I connect to the internet router, and every device is then through that network that automatically appears connected to the internet. And actually, that works. You can build that yourself, and it's pretty easy to do. I'll show you later. So, the architecture is like we have small nodes, cheap, small computers like Raspberry Pis, or maybe even smaller, that do sense the data, that do convert the analog signal, the temperature, into a digital value, and can display that, and can control simple stuff. And if you want to do more with that data or combine data from different sensors, you probably will do that in a larger node. For example, connect all those small sensor and actuator devices into network that into a, for example, Raspberry Pi kind of node that then does processing of all data and communicates that data to the internet and present a part of the security architecture there, because you don't want to have your fridge directly connected to the internet. It can be cool, but there's a certain security risk. Hey, my fridge is hacked because that's a very small piece of hardware that with very small space of software, so the software is not completely featured with all security features you might need. So hey, they hack your fridge, and from that fridge they hack your database that you don't want. So you want to have that separated some way. So I messed up some slides like this. Yeah, that's it. Like you got your sensor mesh and your actuator stuff. Also, you can like have that with your door opener. You have one master node, and then your backend, your database with where you also can do smart things. And in between all those pieces, you have an IP network. Also, you can have an IP network here, where you have your presentation with your nice graphs and your manager's corn. So the complexity goes from here. This is pretty simple, like a node that only can handles that door open, or only can measure the temperature or the humidity, or maybe combine those two and then do something very simple things, to a master node that combines data from more nodes and sends signals back to, hey, that sensor says it's pretty warm out here, that sensor says it's pretty warm, that sensor says it's pretty warm. Well, I'll open the window. Tell that other sensor, tell that other node to open that window. So, we have small sensors, and building that at my kitchen table and with my soldering iron ready to go loose, I used Arduino board for that. The larger nodes, I used a Raspberry Pi, or later I used a Beagle board, which is also a small Linux machine like a Raspberry Pi. And then I connected that to the internet, to some server that did some intelligent things. So what's all about this Arduino board? This is fairly small machine. It's a I got actually with me. Hey, it's hardware. You have to touch it, right? Otherwise, it's not real. So this is well, that's a blue one. This is a red one. A small Arduino board. Here is a small processor. It's a system on a chip, so it has flash. It has RAM, it has a lot of I/O, and it has a small chip to actually connect to a USB port, and there's loads of external connections, like the GPIO connector on the Raspberry Pi, only more. And this board is very well capable of getting sensor data, translate that into some digital value and communicate that to the USB port, or with a small, there's more hardware to come, small board which you can actually stack on it's getting rid, man. Stack on to a UTP connector where you then just can connect your internet to. And this chip on that little board has a TCP stack in hardware. Yeah, well, it's a little simple. It doesn't do IPv6, but yeah, you got that on your local network. And just use private IP addressing, and then go from that Raspberry Pi onto the internet with public IP. But
can it do Wi-Fi?
What?
Is there a Wi-Fi equivalent?
There is a you can put Wi-Fi on. There's a daughter board that you can put on that has Wi-Fi or other networking capabilities. How's that around? So there's also smaller about that. This has got the same processor as that little Arduino board, and this has a little RF chip so that it can communicate not through Wi-Fi but to other these sorts of boards. So like the Arduino, small Atmel system on a chip. It has RAM, it has flash board. It has a lot of I/O to connect these sensors to. It has analog I/O, where there's an analog to digital converter on that, actually on that chip. It has digital I/O, and it has I/O where you can send pulses through, independent from, you don't have to program that. You said, hey, give me a pulse of so many milliseconds, and I'll show you that where that's interesting for. So you have we have different sensors for analog output, like it delivers voltage like with the temperature, voltage rises when the temperature rises on. That needs the AD converter that might be on the chip. And there's a load of sensors that have digital outputs. Like these. This is a small sensor that senses air pressure. This is a sensor that senses light and the color light, temperature sensors, a GPS sensor, and there's just connectors that connect to that Arduino board. And there's loads. I'll skip that. And there's loads of software for that. There's loads of libraries for that to actually connect that piece of sensory equipment to your program that's running on that little board. So if we have actuators, we can output a voltage to actually light a LED or something. We have a digital to analog converter to make pulses, and that can be translated in, for example, sound. We can have simple digital outputs to turn something on, turn something off, turn the light on, turn the heater on, and you also can use servos that translate pulse widths that come out of that board into a position. It's a small motor with a feedback loop that actually translates a certain pulse width into a certain angle, mechanical angle, for example, to open your door or to change your door lock. I'll show you that. It's like that. It's also used in like model planes, model helicopters, to actually change the throttle, for example. And if you send a little pulse to that, then it changes the position of that lever out here. And so you can like open stuff, change things, make mechanical moves. So that you can use for well, for each and every. Well, you can imagine what you can like if the robot needs to raise his hand. You need to have a small servo to do that. Well, the digital I/O, you can take the output pin and wire that to a LED to have a light go on and off. You can have a little switch with a couple of resistors that actually wire to that Arduino, and you can sense, you can have your software react on pressing switches. And you don't need to actually solder that, because there's also little boards like the sensor boards with switches and LEDs and that kind of stuff, so you can like wire that up without using your soldering iron if you're not confident in handling a soldering iron. So, network. There is Ethernet shields, that daughter board that I showed you with the Ethernet plug. It has TCP and hardware, and there's software libraries. There's also Zigbee, which is a network protocol that does mesh networking. So you got 20 of those small boards with a Zigbee shield on that, and it builds the network itself. And then you got one with Zigbee and, for example, your Ethernet, and then you can, through that one board, can address all the others. You got the RF12, which is a proprietary networking device that I showed you earlier on that little tiny board. So, well, this is a Zigbee module. Coming to software, I've got to step up in speed because I'm watching that clock, and that's I'm between the hardware and the drinks, so I got to manage that. You got an open source IDE that's written in Java that you can download, and you can like build your software with that. You can also do the real brave stuff. Bare metal, you take GCC for the GCC cross compiler and a programming device, and you can program that board using the code that you compile, assemble. Then you don't need any bootstrapping because you directly program that chip on the board. Otherwise, the chip on that board, if you use the IDE, should run a bootstrap code that you can download your code over the USB. But most boards come with that pre-installed. So quickly, how do you actually do that? I want to build a sensor for temperature and humidity and connect that to the Ethernet to nudges and switch some lights on 220. So I take a temperature sensor. That's a little sensor that I wire up to the Arduino board with like 3 wires. Then I take that IDE, build some software, take some libraries that you can download, and read from the sensor the temperature and humidity, and I can like print it, but I can also send it through the Ethernet library if I set a MAC address, IP address to a web server that can run on that little board, and then I can like read out with my machine, read out over the Ethernet connection, read out the temperature from a web page. No, well, and then I'll get a HTTP GET to read out that temperature and humidity data, do some awking, and put that into my nudges commands.cfg or your Zabbix. I have to tell that because we got the Zabbix guru here, and display that. To actually do some output, I can use the same Ethernet library and do a HTTP post on that little web server that is running on that small board, and have the fan turned on, the fan turned off. And to use that, I use a device that is a solid state relay that actually has a 220 part, like these 2 connectors, that you can like use as a switch for your 220 or 110, whatever. And then the other part you can safely wire to the microcontroller board. What's happening in there is there's a complete separation between this circuitry here and this circuitry there. There's a small LED and photo transistor here that makes a physical separation, so you don't have the your board directly connected to your mains voltage, which is kind of dangerous, especially if you then connect a computer to it. So you can build interesting things with that, and there's loads of tutorials on the internet. There's loads of tutorials to simply start with turning on, turning off a small light, up to building a complete sensor mesh system with actuators that actually do something and control something. And I really want to, starting on that next year, to do a workshop on that as the NLUUG, to actually get your hands dirty and do this. See that it's cool. See that you actually can program. I'm a hardware guy, and I work in a company that is morally dominated by software people. And those software people only see that little screen. And well, that's cool, right? If you see something change on the screen, but it's really cool if you see something change in real life. Like if you see the light go on, the light go off. And the other thing, that's because I come from the world of electronics, you can also do some smoke signals with that if you wire up it wrongly, right? That's the risky part of it, and well, give some, well, for a hardware guy like me, give some cool thoughts. Well, important aspects in the Internet of Things world is, I talked to that, security. Because we have very simple, very small pieces of software, very small space on that, you cannot, and it's very difficult to get your applications running on that firmware secure. And if you've got loads of them, and loads of them differently programmed, you have to take extra security measures outside that network of sensors and actuators, because that Mr. Hacker not only likes to read from what's in your fridge, but also, if you do that professionally, maybe likes to change something about the water management plans that we have here in Holland, like open the floodgates. Hey, we don't want to have that. Here we are pretty okay, but where I live, there's going to be 6 meters of water then. So be careful about security. And that's a completely different area, and there's a lot of things to do, because those professionally applied environments are not as secure as they say that it is. Well, if you use wireless networking, you've got the complete wireless blah blah that you need to be careful about where to put it, do the antenna stuff. That's a completely different thing. But if you've got very small devices, you don't want to have a big antenna on that. So that's going to be difficult sometimes to line up. Power consumption. Hey, you've got fairly small devices, so you can actually power them from a AAA battery and run that for like a year if you write your software on the right way. Because there's timers in that chip, you can put the chip in sleep mode and have your program wake up like every 10 minutes and then do your measurements and send your measurements onto that Arduino or that Raspberry Pi board, and then put the thing in sleep. So you can. I got a small measurement device like that one, powered from 2 small penlight batteries, and I stuck that under my floor to measure the temperature and see whether there's water under my floor. And that runs already for like 2 years from like 2 batteries. And I put it into sleep and then measure it once an hour and then communicate that through the wireless network. So I said, like, distributed processing, have sensor data, have actuator data on that small machine, communicate that to a smaller or a little bigger, like Raspberry Pi, where you can like do everything you want on your favorite Linux platform, and then communicate that to the internet. Have that distributed. And then all of a sudden it becomes more and more applicable to small spaces, larger networks, because these things are cheap. Like, it's like 10 euros, 20 euros, you got a small board, and you can go ahead and go play. So that's the thing that I want to say. It's really simple, no difficult soldering required, simple software. There's libraries all over the place. You don't need to be a software engineer and know everything about OO programming and Java and all that. No, it's very simple. We can all do that. And if you come off of that platform, go onto a Unix platform, and then we can do everything we know what to do, like scripting, Python, everything. So networking is easy. Everything is already thought out. You just have to put in an IP address and put in your data, and up you got a web server. Sorry, I don't have a demo because it was like heavily busy last week. I was planning to make a demo, but on that workshop we'll have demos. We'll have great demos, we will be building them. So, I think it's about world time. That was what I had to say. Any questions? Yeah?
In my experience, the hard part is not to connect the sensors and the actuators, but to actually have a piece of software that lets you build the flow of the thing you want to automate. And
well, that piece of software is called creativity.
I know there's 4 or 5 initiatives, and 4 years ago there was only Mr. House written in the most beautiful language there is in the world, which a lot of people don't understand. Yeah. But now there's a whole load of other systems that you can use. Have you looked at those?
But yeah, I looked at those and I thought, well, why doing that? Why trying to make it so easy by making it difficult and making it difficult to handle, while we just can do it ourselves, right? We as community NLUUG can actually simple program those things, and the language that is used into that Arduino stuff is very simple. You don't have to go do C. There is no pointers. So, and actually, those making that step from the software to the real world and thinking about that and having your creativity at work is much more difficult to come up with, wow, this is the great thing, than actually programming. And there's loads of initiative to make it simpler on the programming side, but there's no, well, initiatives of coming up with great stuff. That's just you. Imagine and go build.